Okay, so I'm going to talk today about a paper that I co-authored with my colleague Colin Klein from the Australian National University. And we are both the members of the Humanizing Machine Intelligence project here. If you're interested in reading the full version of the paper will be published at the proceedings of AIES 21. Or if you want to have a preprint of this paper, please send me an email and I'm going to share that with you. So we're going to talk about the ethical gravity thesis, Marrian levels, and the persistence of bias in automated decision-making systems. And let's start with an example. So assume that you are a programmer and your job is to make a system that determines eligibility for high-interest payday loans. So your employer is predatory and the customer base is vulnerable. In order to maximize profit, you must identify individuals who will never quite be able to repay their loans, but for whom that burden also will not result in bankruptcy or suicide or other drastic problems. So having been deeply enmeshed in the literature on ethical algorithms, you decide that you ought to make the system more ethical. But how would you do that? So the ambiguity in this question should be really obvious. On the one hand, you can make sure that you do not introduce any new ethical problems. You might avail yourself, for example, of any number of proposed metrics for measuring algorithmic fairness and ensure that you optimize one or a few of them. Or you might blind your data set to avoid information about protected attributes. You might ensure that, for example, you provide a detailed model card that specifies all of the information used in building your model. On the other hand, what you make will lead to substantially immoral outcomes. And that is true no matter how careful you are. The design goals of the system at the first place put a fundamental upper bound on how ethical the result of your algorithm design could be. So more generally, discussions of automated decision-making systems, and I just should clarify, I'm going to use the terms automated decision-making system or AI systems kind of interchangeably in the talk today, despite the great kind of point that Joshua made in the previous talk, but just take it as like examples of AI decision-making system, automated decision-making system that I talk probably for the purpose of the talk. It doesn't matter. I'm not careful with the terminological choice. So the discussions of automated decision-making systems often contain a wealth of different concerns with the relationships between them be unclear. So some authors are really concerned with the ethical deployment of technology. Others are concerned with details of algorithms or other mathematical objects. And still others care about the details of particular implementations, where data sets come from or who gets paid for annotations. And the relationship between these different projects is often obscure. And so the effectiveness of particular interventions is difficult to really evaluate. So in this talk, I'm going to argue for a particular thesis about the relationships between these different ethical projects, what we call in this paper the ethical gravity thesis. And in order to make this thesis precise, I need to do a little bit of work. But for now, take it as a thesis that ethical problems at higher levels of analysis of an artificial intelligence system can't be reliably ameliorated by interventions at a lower level of analysis. And the toy example that I started the talk with, the payday loan case, wanted to illustrate this principle. But I talk about the levels of analysis or thinking about ethical problems at different levels of analysis. And it's good to, of course, say what do I mean by that. So the ethical gravity thesis more specifically makes a claim about dependence relation between different levels of analysis of an automated decision-making system. And what are those levels? There are many different ways to think about this level-based analysis. There are many different frameworks out there. But we are going to use a very famous and influential framework in cognitive neuroscience by David Marr, in which he used this framework in order to give an analysis of complex information processing systems. So Marr, in his analysis and a complex information processing systems, for example, you can think about visual, like the way we are doing visual processing. He identified several levels that are common to the analysis of any computational system. And say the goal is that you want to know why vision works the way it works. And then his very rough idea was that in order to properly provide an answer to this question, we need to analyze this system, computational system, from different levels of analysis. And his framework originally really was to account for different levels of analysis, again, in cognitive neuroscience, but it has had a very broad influence across many different fields concerned with computational explanation. So in science and philosophy of science, this framework is very popular and important, and that was a motivation for us in the first place to kind of see what this framework can say about ethical decision making in the context of algorithms and automation. So Marr posits 4 levels of analysis at which any computational process can be approached. So here you see the Marr levels, and then here we have some corresponding algorithmic decision-making levels. So say more about that. So Marr's levels were initially offered as a way of, as I said, understanding and explaining early visual processing. So the highest level of analysis here, the functional level, is a characterization of what goals the system aims to achieve. And we call this the functional level of analysis. And there are different commentators who say, actually, Marr didn't talk about functional level. He started just by talking about computational level. In the paper, we kind of discuss why we take this functional level to be also an important level. And I would be happy also to talk about that in the Q&A. So the functional level of analysis of an automated decision-making system correspondingly kind of reveals overall business or political project. Take it as a pre-technical description, the sort that could be offered to executives or marketing or sales. And this could be something like the risk of balancing the risk of recidivism with the need to parole, or figuring out who to give loans to in order to maximize profit. So in the case of like a natural system, it's going to be about the visual processing, for example, the everyday experience, the coarse psychological, psychophysical demonstration. So basically, the functional level, like very roughly, is going to say what a system must do in order to count as a successful system. And of course, we might sketch the function of a system here in a very short elevator pitch. The full functional specification of a system normally depends quite a bit on the context. So for example, nobody gives out loans in a vacuum. The practice of loan giving is made possible by a host of other regulations and expectations and social practices that shape this process of loan giving in various ways. So we include all of these contextual effects in the functional level of analysis of an algorithmic decision-making system. The second level is called computational level, and basically it has to do roughly with the computational problem, or another way to put it is the mathematical formulation of the problem. So the idea here is that any automated decision-making project can also be understood as attempting to perform a certain mathematical task. To determine which loans to make might require the simultaneous optimization of one or more equations, or recognizing objects in pictures is formally equivalent to untangling manifolds in a very high dimensional space. So the idea is that there is a very nice and clear correspondence between this level of analysis with respect to complex natural information processing systems and the algorithm decision-making systems. So some of these computational processes are learning processes, and there the real task is to find an appropriate mathematical function from data to another function that will provide answers And some of them, however, they're like more sophisticated mathematical formulations of the task you want to do. Okay. So the third level of analysis is algorithmic level. So in the computational level, we said that basically this level has to do with a mathematical formulation of the problem. So if you have an algorithmic system or automated system that is going to recommend or assign loans to people, if it's deployed in a bank, for example, of course, this system works through a particular mathematical conceptualization of the goal that it has to satisfy. But these mathematical functions, if you're some sort of realist about mathematics, are timeless. So to get a computer to do something, we need an algorithm. We need an algorithm, and many theoretical computer scientists say it's kind of impossible to give a proper definition of algorithm. But roughly, an algorithm can be thought to be a set of rules or directions for getting a specific output from a specific input. And so these algorithms, of course, prescribe a sequence of steps and operations that must use time and other resources. So the algorithmic level of analysis with respect to this like natural, more Marrian information processing systems has to do or is concerned with specific representations, specific algorithms. When we come to the domain of algorithmic decision-making, this automated decision-making also faces a variety of different kinds of algorithmic choices. So the specific choice of an algorithm, say a greedy algorithm or a jigsaw algorithm for optimizing a given mathematical function, can make a drastic difference to how accurately or quickly the function is going to be computed. And it has long been known, for example, that even like poor quality linear regressions can often outperform humans on some simple decision tasks at trivial computational cost. Whereas if you want to make further improvements in accuracy, that would require rapidly increasing investment of resources. So this algorithmic level really has to do with all these kinds of details, but also the representation of data. So let's assume, or let's consider this following example. If I represent my loan applicant's data as points in a high dimensional continuous feature space, I will have available many more and more accurate classification algorithms than I would if I would represent each applicant as a simple dictionary of categorical properties. So this algorithmic level with respect to algorithmic decision-making has to do with all of these specific algorithmic details and also the representation of the data, because the choice of the algorithm or the way the algorithm is going to perform would depend on that. If you're having, for example, a supervised learning algorithm or machine learning algorithms more generally. And the last level of analysis is basically about, so the first three levels were kind of hardware agnostic. The last level is about the implementational level. So for example, there are many different algorithms that can learn to recognize faces and emotional states that they represent, but to run them for predicting the emotional states of unobserved faces, we need to train the algorithm on a data set of faces. And then how this data set is designed, what it includes and what it doesn't include, kind of relate to how we are going to implement this algorithm. So we claim what is important about this implementation level is anything that is relevant to the instantiation of an algorithm as a token process, not just the hardware. And you might disagree with us when we presented this paper here to some of our colleagues. They kind of disagreed with us. So we provided a justification for why we are going to include all these details of programs data collection into our paper. All right, so far it was just not a talk about the ethical algorithms or ethics and ethical and social implications of algorithms. It was really a talk about basically the outcome of this, what I presented so far, says that when we want to think about an algorithmic decision-making problem, we can think about that from different levels of analysis. And correspondingly, when we want to think about the ethics or social problems with algorithmic decision-making, we can use these levels in order to talk about different ethical problems or social problems that map onto these levels of analysis. Okay, so we can have a level of analysis for ethical problems or social problems more generally that occur at the functional level of analysis of an algorithmic decision-making system. And I go into the details, just want to say how this level-based analysis is going to get relevant to this ethical gravity thesis that we're going to argue for. Okay, so now the ethical gravity thesis can now be stated more precisely now that we have this level-based analysis of algorithmic decision-making systems. So the idea here is to say that if an ethical problem arises at one level in the Marrian hierarchy, one should expect it to persist at all lower levels. So lower levels can introduce new ethical problems, but one should not expect them to get rid of the problems that are inherited from the higher levels. And this is true even when people responsible for creating or maintaining the lower levels have a sincere and strong incentive to ameliorate ethical problems. The idea is that if the problem is difficult or there's an ethical problem coming from the functional level, we can't design a super ethical algorithm at lower level, whatever that means, at the computational or algorithmic level, and say that this algorithm in a robust way is going to resolve that ethical problem. So to put it more concretely, back to the payday loan example, insofar as making a payday loan system is ethically problematic at all, the ethically problematic features don't go away when you make a particular version of that system. So the lower levels might tack on additional ethical problems, but they can't really avoid the ones that are inherited from the functional level. So this is one idea of this ethical gravity thesis, and then I'm going to provide an argument for that. But before I go further, I want to provide two qualifications or clarifications. So first of all, the ethical gravity thesis is phrased in terms of reasonable expectations. So there may be some isolated or random examples in which lower levels solve ethical problems that are introduced at higher levels, either intentionally or accidentally. But this ethical gravity thesis claims that such instances are neither frequent nor particularly robust. Second, when we talk about ethical problems, those should be understood extensionally. So there's a problem. When we say there's a problem, it means that it is not really coming necessarily from a bad intention, but there are bad consequences. So ethical gravity thesis is really about the consequences. So we provide two arguments in defense of the ethical gravity thesis. The first one, we call it the realization argument. And the second one, we call it the institutional argument. So realization arguments in a nutshell says that, so if you remember when I presented, let me just go back to the slide, these levels, there are these arrows that kind of show some relations between these levels of analysis. And here, with respect to a realization argument, we want to say that the nature of these arrows can be understood as being realization relations. So what are realization relations? They say that, so realization is a relationship of asymmetric necessitation. And this means that B realizes A, just in case being B is a way of satisfying A, but A does not necessarily require B. So the realization relationships then between levels require lower levels to faithfully perform the task as specified at higher levels. And this means that an ethical problem that can be identified at one level should be expected to be preserved at all lower levels. But to make this notion of realization relation more concrete, let's consider a non-ethical kind of concern. So if I have a list of books and I want to alphabetize the list of these books, they have names. This is a functional level statement of the problem. What is the goal? The goal is to alphabetize the list of the books that's given to me. To solve this, I need a function which takes a list of book titles and then returns a lexically sorted list. And doing this is a way of satisfying the functional level statement of the problem. So the functional level problem does not determine the computational level function. It doesn't tell me what kind of mathematical function I have to use in order to resolve this problem. There are many different sorting functions, and they would deal very differently with, say, duplicates or non-Latin characters. So there's a relationship of asymmetric necessitation between the functional level of this sorting problem and the computational level. So performing a particular sort function is a way of alphabetizing books, but the requirement to sort does not necessitate any specific kind of particular function. So you can have many different kinds of functions. Similarly, again, we come down this hierarchy. So having specified my function, I can use many different algorithms, let's say selection sort or quick sort or many other options in order to perform this task. And again, having chosen an algorithm, I still have flexibility in the programming language and hardware, like related to the implementation level of analysis. So the realization argument, therefore, is very straightforward. Suppose an ethical problem with negative impacts appears at a higher level of analysis, then the solution to this problem at a lower level of analysis is a way of satisfying the ethical demands that appear at the higher level. And then the next lower level of analysis might asymmetrically necessitate that higher level. And that is just what it is to realize that higher level. But part of this asymmetric relationship is preserving some extensional fidelity to the activities at a higher level. Then the lower level must just have the same effects at the higher level, just in a more specific manner. So lower levels must do everything that higher levels do and more besides them, right? Because they're going to make it more specific, they're going to make it more operationalizable, of course, from different perspectives of analysis. And so then by induction, the problem will persist from the high level to the lower level. In addition, because this realization relationship is one of asymmetric dependence, there is considerable flexibility in how any level is realized at a lower level. And this means that lower levels can still introduce new ethical problems. So a lower level can, for example, with respect to a perfectly reasonable facial recognition algorithm, we can implement an ethical task that might still go astray if trained on a biased data set. So lower levels preserve the ethical problems in a nutshell, but also they can add more besides them, which is just what the ethical gravity thesis say. So this is an argument in defense of the ethical gravity thesis, the realization argument. The second argument, we call it the institutional argument. And very briefly, it kind of talks about the active social and political forces that make even unsuccessful realizations relatively infrequent and difficult to maintain. So again, remember the realization argument establishes that ethical problems go downward when the realization is satisfied. And realization is satisfied because that's the way this level of analysis of Marr is adapted, or we adapted that for thinking about ethics of social considerations of algorithm decision-making more generally. So computers, however, make a variety of different mistakes, say that a higher level is partially realized by a lower level, when the activity of a lower level necessitates the prescribed effects of the higher level across some, but not all contexts. So remember the sorting algorithm again, it might realize our sorting function, except for cases when some Cyrillic characters appear or something like that. So it's possible for these algorithms, of course, automated decision-making systems to make mistakes. And those who work on the development of these automated systems know how common partial realization is. It is particularly common in complex systems and also morally laden decision-making systems. Those seem to be also examples of very complex systems. So one might hope that negative effects that would otherwise occur due to constraints at higher levels, they might be partially ameliorated by lower levels. And this might occur by accident, or it might occur via some sneaky actions of a clever and motivated programmer who's determined to undermine the system. Or it might also occur by sheer deficiency and inertia at the implementation level. However, we don't care however it happens, but one might hope that these mistakes could fix some of the otherwise problematic aspects of a system. And this is a tempting thought, but we want to kind of say that it is unlikely to be a particularly effective approach in practice, because there are many institutional constraints on the creation and maintenance of automated decision-making system. So an institutional constraint is any set of procedures or processes that tends to move partial realization to a full realization by correcting errors and so on. And the key point then here is that partial realization is really a kind of failure, according to the institutional pressures. It occurs only when the way of doing some activity does not completely align with that activity across all the relevant contexts. And there are a variety of institutional constraints that exist in order to catch errors of this sort. So I'm going to consider two sorts of institutional constraints here, but they are just illustrative. There could be many more in different contexts. So the broader point, basically, that this argument wants to make is that the existence of some institutional constraints means that some substantial partial realization should be relatively rare and fragile. So the first kind of institutional kind of constraint can be thought with respect to the development of complex software projects. For example, modern software projects, whether they're commercial or governmental or open source, are usually embedded within a fairly complex system of procedures and practices. Those procedures and practices are designed to catch and mitigate the bugs, for example, when the software is being developed. And this includes practices such as unit tests, code reviews, bug tracking, and version control. These are meant to minimize the occurrence of partial realization at the algorithmic and implementation level. And the second kind of constraint, so if you think about automated decision-making systems as socio-technical entities, there are many different arguments in favor of that, is that these automated decision systems also arise themselves arise from and are maintained by various social and political forces. So remember again the payday loan example, toy example that we started with. The existence of some high interest payday loans does not really occur in a vacuum. It's just that there are very different kinds of concerns about economic perspectives and economic success and social automation, and how that brings more efficiency into practice, and all of these social and political concerns justify or push for the design of this system. So these different institutional pressures, therefore, may have different effects at different levels of analysis. So broadly speaking, technical and procedural institutions work to correct partial realization. They want the system to do exactly what it's supposed to do. And when the system is, we have an algorithm for that, they want this to completely satisfy what the higher level necessitates. And then economic and social constraints, on the other hand, are more operative at the functional and computational level. So there are different sorts of institutional forces, but they operate at different levels, and they could be thought to be different. So before I go to an example, therefore, the proof for our for the existence or for in defense of the ethical gravity thesis is now complete. We say that full realization from the realization argument ensures that ethical problems are inherited by lower levels. Then partial realization does not last for long. So ethical problems are either faithfully preserved by the lower level, or else the fix is unlikely to last long. And that's what we just claimed by the EGT. So in the paper, we are going to, first, so far this was a little bit kind of abstract. It was like a philosophical argument in two philosophical arguments in defense of the ethical gravity thesis. And in our paper, we apply this ethical gravity thesis into 3 case studies. I'm going to talk about just one of them today, which is the case of the allocation of medical resources. So some algorithms reflect ethical problems at a broad societal level. However, the ethical gravity thesis also allows that lower levels might create some new ethical problems, either directly or unwittingly. So one very famous work about the problems with this allocation of medical care resources that I very much like is a paper by Obermeyer and his colleagues, and he and his colleagues did an analysis of healthcare allocation systems. So they look into some automated systems that run across many different hospitals in the United States. And these automated systems attempt to allocate scarce and costly healthcare resources to those who would benefit from them the most. That was like the functional level goal. So the broad goal, again, corresponds, if you remember that level, this statement that they want to kind of maximize the allocation of resources to those who are the most in need, is a functional level problem. And this is not, let's assume, in itself an ethically problematic objective. Now, Obermeyer and the colleagues showed that the algorithm in charge of this resource allocation task was largely driven by translating the problem in terms of predictions of healthcare costs at the computational level. So we have a functional level, the computational level. And at first glance, this is unsurprising, as I know cost and health needs are highly correlated. So that's maybe the right way to go and do this translation. However, in the context of the society of the United States, there's also a background correlation between race and healthcare costs. So on average, Blacks receive less care for a given level of need than do whites. And because of that, the algorithm tends to dramatically underestimate the need for additional care among Black patients. So together, these facts mean that Black patients were less likely than whites to be referred to support programs for patients with complex medical needs. And according to the way the system made the allocation, only 18% of patients that the algorithm assigned to receive extra care, they were Black. However, if the algorithm would have thought about this correlation, would have considered this correlation, this figure should have been closer to 47%. So back to this, our ethical gravity thesis argument, this study shows that the ethical concerns for the allocation of healthcare resources persist at the lower levels of automated decision-making. If at the functional level, we haven't defined the problem properly, we haven't taken anything into account, no mathematical functional algorithm at lower level, again, in a robust way, is going to resolve that ethical problem. So even this decision-making system, so let's say that we want to instantiate the institutional argument for this case study. It says that the problem comes from using what seems like a plausible proxy for healthcare costs that interact poorly with the other background facts. So Obermeyer and the colleagues say that accurate predictions of costs necessarily mean being racially biased on health. And the discussion around this phenomenon so far, as we know, assume that this bias is kind of straightforwardly bad. So this is there is a subset of patients for whom the algorithm therefore performs poorly, and that poor performance is really bad for the individual patients and bad from an economic point of view. that untreated medical conditions tend to get worse and more costly. So then the ethical problems with respect to this case arise not at the functional level, but at the computational and algorithmic levels. There are specific instances of the problem formulation problem concern that Pasi and the colleagues in a paper from FACT, I think 2019 mentioned. So building an automated decision-making system involves a series of what they call difficult translation, and these include the move from policy objectives to specific algorithms, the choice of objective functions, specific features that are used for problem prediction, etc. And one might worry that certain kinds of ethical properties can't, in principle, be satisfactorily mathematized. But one might also worry that even among those properties that can be satisfactorily mathematized, there's still some additional ethically laden questions that must be answered. So in short, we hope that this ethical gravity thesis and this level-based analysis of ethical algorithmic decision-making provides a framework for locating different social and ethical problems with automated decision-making at the right level of analysis. Again, in the literature, there has been many different people pointing out that there are these different kinds of problems, and we don't say that that statement is by any means new. Many other people before us have pointed that problem, but we think that this ethical, framework, the Marrian framework, allows us to locate these problems at a right level of analysis and provides a more organized conceptual framework for making sense of the relationship between these projects. And also it kind of shows that, again, we can't have really these technological fixes. The arguments, both of the arguments, the realization argument and the institutional arguments, wanted to make a case for that. And of course, it's just the first start. And we think that there should be many more research to be done on the role of upward constraints as well as downward realizations and how these perform exactly in many different contexts. Yeah, and thank you very much for your attention.